on my local drive. Okay. So so this is a missing V here. You can so you can actually derive these equations for the conservations of total energy for simple harmonic motion. Okay, so it should be mv dv dx equals to minus kx. So I have made a corrections to the assignment 8. The correct solution should be like this. Okay, so if you have submitted, could you submit again? I think this is a wrong equations. Okay, so I think you should make the corrections to this. So it is not correct to have just m dv dx equals to minus kx. Okay, so if you have submitted, please correct it. I think you should still have some time. Okay, so I think I save it. So the notes that is shown on my screens is supposed to be synced in my Google Drive. So it should be automatically corrected. Once I correct it on my screen, you should be able to correct it. Okay, so for those who attend log in late, I'll let you to do the. For those who log in late, I'll let you to do the attendance maybe at 4 o'clock. Okay, so you should always have time to do this. So people, I think someone, if you have not switched off your mic, you could switch off your mic now, unless you have something to ask me. Maybe before I begin talking, once I start to talk, maybe we will just keep on going and going. You might be very tired. So before I start on my continuous lecture, I would be happy to hear from you if you have any problems or any query that you want to ask about the course, the overall progress. I think we are nearing towards the few final topics, right? So the second law of dynamics, which is the Newton law, and the solution to second order differential equations is kind of difficult, right? So we are getting close to the end. So what I'm planning to do next is to help you to do some simulations of dynamical system, right? So equations that is a Newton law governs how dynamical system change with time. For example, you have planets orbiting a sun, right? Or you have the sun in the middle, Earth orbiting around the sun, and moon orbiting around the Earth. So they are evolving mechanically and it's governed by Newton's law. And you can write down the Newton's law. Then you have a set of equations that would be in the form of second order differential equations. And using the technique that we have learned so far, you will be able to solve the second order differential equation and to predict what is the locations of the orbits of the planets and the moon on the orbits at any time, like from t equals to 0 up to, say, t within a year. So the solutions of this provides you with an insight of how the system evolved as a function of time, and this is a result of the dynamical law or the equations that governs their evolution, which is basically the Newton's law. So you put in different initial conditions, then the system will start to evolve. So once you have a numerical solution, the next thing you can do is to visualize it. Right? So you can visualize, so far we just plot the graph of the solution statically. Later on, we'll try to simulate how you can see the dots move around in the orbits. Then, if we have time, we will be going to talk about a Valais algorithm. The Valais algorithm is a more powerful numerical method, which is not provided by Python, but we have to write our own code. So Valais algorithm is just another way to solve second order differential equation involving Newton's law. So every system that is evolving according to Newton's law could be solved using the Valais algorithm, and the Valais algorithm allows you to time steps the Newton's law so that you can see how these systems evolve dynamically. The difference between the Valais law, the system between the Valais law and the ordinary differential equation that we solve second order is that Valais algorithm is much more general, right? So as long as you have a force, tell me the force. As long as you provide the form of the force, then you'll be able to time step the system. So let's see how it goes. So that would be the most interesting part. So one of the important objective of the 1.1 is to learn how to use Python to simulate physical systems that is evolved under the physics, right? So there is a lot of details and technical knowledge you need to learn, like for example how to write your code, translate the equations. So these are all part of the exercise, part of the training. So I suppose the course of 1.1 is slightly different, but very different from other courses you have learned, where you have to really know how to write out every single steps. You have to know the syntax, you have to know how to manipulate the computer, you have to know how to download the code and how to arrange your logics, and then finally give me the final answer. And after you have finished the class of 1.1, you'll be able to do a lot of things with Python, right, for your future, right, especially in data manipulations, or if you were to learn physics or study physics if you know the dynamical law. Okay. So let's go on to the our lecture. We are now, for those who are coming in late, I'm sorry that there is a mistake in the simple harmonic motions. In your assignment 8, the equation should be mv dv dx equals to minus. So a v is missing. The v is missing. So please, for those who have already submitted, could you please submit again, or if you have not, just make sure that you use the correct equation. So I suppose detecting wrong equations for me is also part of your training. So I always make stupid mistake, and one of your job, take it as finding my mistakes. Okay, then let me know. Now if you do not spot the mistakes and everyone will keep quiet, then both of us will be okay. Let's see. Someone say this. Yeah, the solution is correct. So the solutions is it correct? Not quite. Now someone is showing you. Cherise is showing me the solutions. Now before you solve the equations, what you should expect is that simple harmonic motions has a solution, right? So the potential functions of a simple harmonic motion should be Vx, not V. No, this is V. Let me see, Vx. Yeah, not quite. This is not true, because if you look at the screen now, I think everyone can look at the screen, right? So it's good that you send me your solution. So now what happened is that at v equals to 0, that is at time 0, you are releasing the pendulum from rest. Am I right? So when you release it, it should be 0, but not 1. So let me check again the solutions. The question is asking for v naught equals to 1. Yeah, okay, so no, you're right, I'm wrong. This is, now my original plan is to set v at 0 equals to 0, but since I already give you 1, then it should be 1. So just stick to 1 instead of 1 of 0. So usually when we do a pendulum, we release it from rest. Right? So in that case, v at 0 should be 0. But if you do not release it from rest, that is when you release it, you give it a kick, that it has a velocity of 1 meter per second, positive directions. Then v naught at 0 should be not 0, it should be 1. So your solutions, let me look back at your solution. Your solution is making sense because when you release it at 0, the velocity is indeed starting from 0. So you have to solve separately for x and negative x, and I get the right solution, but I still get an error warning. There is an error. So okay, let me, now since we are discussing the tutorial here, it's good that we spend some time talking about it. So first of all, I check your answer, right? So your answer here is correct because it has the initial condition to be correct. At time equals to 0, your x is 0. No, yes, no, yes, no. Okay, let me see again. Now, at the beginning, your displacement is at 1. and the velocity at the beginning is 0. So this is supposed to be the initial condition. At time 0, your x is supposed to be sitting at 1, and v0 should be at 1. Okay, so let's come back to here. So yeah, it's indeed that at x equals to 0, your v is 1.4. So that is something not right, isn't it? Because according to the initial conditions, when t is 0, no, sorry, this is to say that when x is 0, when x is 0, your v is 0. Okay, so I said it. Let me repeat it again. Now this is a function to be solved, v as a function of x. So there's no time here. So at x equals to 0, the velocity is 1. Okay. Now I'm coming back. A few minutes ago I was thinking in terms of the pendulum changes with time. Now this is not true. These equations only solve the pendulum in the so-called phase space. That is the phase space made up of velocity and position. There's no time involved. Okay, so this is to say that you have a velocity that depends on the position, and when you swing through the 0 position, when x is 0, the v is 1. That means it is not sure whether you are releasing in from rest. Now in this case, the initial condition of x naught equals to 1 and v0 equals to 0 does not means you release it from rest. Sorry, someone is calling me. Okay, so let me think about this. So the velocity at x equals to 0 should be 0. So I think there is some problem with this. Let me have to think about it. x0 is 1. But here, what is saying here is that the velocity at the position 0 is 1. So there is an inconsistency in the initial condition. Okay. So there is an initial condition inconsistency. That is to say, the initial condition is x0 at 1. So the velocity at x0 should also be 1. x0. Okay, I think this should be not 0, but should be x0. So the initial condition is that v at x0 is 1. I think that was more relevant. So if I say this is v at 0, that means when x is 0. So which is not quite true. Okay, so you take the x0 to be 1. So initial condition is that when v is at 1, so when x is at 1, v is at 1. Okay, so then in that sense, the x0 is actually irrelevant. Okay, so x0, sorry, not to say irrelevant, x0 is just a constant. So the condition should be v at x0 equals to 1. And your x0 begins from 1. So when you solve it, you start from x0 to 0. Okay, so there is some questions that needs to be solved here. Okay, so maybe I should explain a little bit. So maybe we spend 15 minutes on this question so that you can understand it better. Okay, so let's just try to solve this on the spot. Okay, so it's 3, 15, 16 now. Let's solve these equations. So you can use this as a solutions. Okay, so let's see how you do it. So first of all, we need to solve this using x0. So x0 is a number which is 1, so it's the initial condition. I need to import sin pi dot integrate from SciSpy integrate import IDE no import not IDE import ODE integrate. Okay, I think that is what we want. Then this is initial, and usually we also have to integrate. We have to import from import matplotlib dot pyplot as plot. Okay, then this is the initial conditions, and then we have to define the model, right? So the model would admit the variable of v, right? So we are going to solve v. No, we are going to model is not. Model is emitting a variable of x. Then we're going to return the model to be v dv dx. So so this is to translate into a form of dv dx equals to minus k over m x over v. Okay, so we are going to the model is a function of x, and then we are going to have k minus k over m. Okay, so k over m, so m is a number, k is a number, k is 1, m is 1, times x over v. So x over v over v. Okay, so v is the input parameter. I think this is v. Okay, I think this is the model, right? So we put in the independent variable, and the dependent variable is x. So this is our differential equation dv dx. Right? So the model returns us dv dx, where v is what we are, well, dv dx. Okay, let me save it so that you can see it on your screen as well. So dv dx is minus k over m times x over v, and then we are going to return dv dx. Okay, so that is how we do it, and then the solutions of v is given by ODE integrate, and then you have, of course, model as your input, and then you have to provide the initial conditions. I keep on forgetting. Okay, I'm sorry. So let me check on the syntax model. Why is that problem? Model vx dot okay, define def. Okay, so that is more appropriate. So what I want is to recall the use of ODE integrate. Okay, so ODE int. So here I have to import this one in order to get the help file to come out. Okay. Help ODE int. So the help file says that I have to provide the function yt. Okay, so y naught is the initial condition. So I just have to remind myself how to use this thing. Okay, so to obtain a solution, I have to provide the initial condition. So here the initial condition is init condition, and then it should be in a tuple. So what is this? This is to be okay. So this tuple is to be maybe I should extend the assignment deadline so they can submit it again, since this is my fault. Okay, now remind me to do that later. So the initial conditions is it. So what is x naught? So the initial condition according to the questions is, okay, this is assignment. So initial condition is v at x naught equals to 1. So the x naught is the initial condition. So the v at x naught is 1. So x naught is 1, is already done. So the initial condition is x naught. Okay, I think this is what it means. X naught equals to 1. Sorry, no. X naught is just a constant. Okay, so the initial condition should be v naught. So the v naught is the initial condition. Initial values of the velocity at v0 and is 1. Okay, so this is the initial condition, not x naught but v naught. Then this initial condition has to be supplied into the ODE. So this is to say that these values of v naught is to be going into here. No, this is model. I have to recall what is this. So okay, yeah, I think this is to say the initial conditions v naught is going to go into v. Okay, so there's only one v. So v0 is going to replace the values of v at the beginning, and then we have to define our x. So this to be a bit okay, so what is our x? X is an array, right? So the x is an array. Now this is a trick, right? So just now there's a questions from this so now you have to solve negative x and positive x. So let me try to explain to you these questions. Okay, Charisse. So let us put in the x separately. The x is to be going from NP Lin space. So now this is a trick, okay? As I mentioned, in solving the first order differential equation, the initial condition should always begin with your x naught, right? So this first number should always be the initial independent variable. And you start off with x naught. And then where do you go? You go to, so x is 1. So then when you want to go? Go to, okay. Now, this question says the x is a variable that is oscillating between minus x naught and x naught, but you put the x naught as the initial condition. So this is tricky, right? So the x naught does not begin from 0. Now this is a trick, right? X is a variable, independent variable, does not starting from 0. But what you expect is that the x naught, the x is going to oscillate between positive 1 and negative 1. Right, so the initial condition is that x naught is at 1. So you begin at 1. So how much? So you see is actually 1. Then where do you want it to go to? Right, the initial condition is at 1. Then what is the next values of x? To 20, 20, 25, 0, whatever. So what should that be? Right, but your condition is that if you were to do the simulations, you expect that since the energy is conserved in the harmonic oscillator, and its x naught is 1, it means, now if we look at this initial condition, it simply means the x naught would oscillate between minus 1 and 1. Okay, I think this is basically what it says. So the x naught is supposed to be the amplitude of the oscillation, right? So you have the amplitude oscillations, then it would be like this. Now I have to check because I have not checked this very carefully. So energy has to be conserved. If energy has to be conserved, then half kx squared must be equals to a constant. So that would mean, so if the v at x naught is 1, that means half mv naught squared is half 1. Okay. Now if you look at these questions, if you check at this one, total energy in the system is given by what? In the system is, the total energy is just given by 1 over 2 times m v naught square. Am I right? Okay, let me show you what this means. So given that the initial condition that at x naught equals to 1, x1 equals to 1, no, this is not quite, This is not quite true. Okay, I think I have to think about this in more detail. But never mind. Can you just follow me? Okay, so let us forget about energy conservation, and then let us put in this one, the lim space starting from x naught. Right, it has to be from x naught, and it has to be 2 minus x naught. Okay, I think that is. Now I'm not sure whether this is allowed because you start off from 1 and then you end in minus 1, and then if you say this is say 200, maybe 10. Let's say it is 10. So I've never tried this before, but I would like to know whether am I allowed to have an x that is beginning from 1 and then end in negative instead of ending at a number which is larger than 1. No, there's an error. So I'm not allowed to have, I think I might be allowed. Import num p as np. X naught is equals to 1. Yeah, I think I'm allowed to assign that. So x array is just a number that starts from 1 and then you end up with minus 1. So the problem is that you have assigned the linear space to be like this. So if this is the case, then it will be correct. Right? So the first number in the linear space is 1. And the initial condition is that when x is equals to x naught, v is equals to v naught, and v naught is 1. Okay, so this is a 1. So what I'm doing now is just to slot in this initial condition. Okay, I'm slotting in this initial condition correctly. So x naught has to begin at 1. So that is how I do it. Right. So okay. So this is the trick. V naught, x naught, and then go to minus x naught, and then 10. And then initial conditions is this. So let me see if this works in neat conditions. Okay, so it seems to be working, not working, something is wrong. Argument t is not given. The argument t is just the x arr. Okay, so there's no error. So let us plot. Now what do you expect before you plot it out? Now what you expect is that it will be a graph that is similar to that shown here. Okay, so are you expecting this as your functions? When the oscillator moves towards the center, right, when x is equal to 0, so this is the center, and this is the x naught, and this is minus x naught. So when the velocity moves towards the center, do you expect the velocity to be high or to be low? Right, it should be high. Right, so this is 1, and this is 1.4. So that means this is to show that when pendulum moves, it is moving towards the center, and then it will be quite fast. So this features is correct. But then there's some problem. I think there's some problem with these questions as well. So when x naught is 0, yes, it will just, when it moves to the center, it's very fast. When it moves towards plus 1, its velocity would drop slightly, right? So from here, it would drop slightly. And then it stopped here. Now what happened after this? Do you think that it will just stop here and then go back in the opposite directions? Yes? No? No? Right? No, you won't, because you expect that when it swing to 0, and it will be fastest. And once it swing to 0, when it's fastest, it will swing towards x naught. And then what happened? That it would slow down, right? But when it arrives at x0, x naught, would the velocity be 0? No, it won't, because it will be 1. So this is true. So this is correct, because this is initial condition. But my question is that, would it continue to swing beyond x0? Would you think that it will swing beyond x0? In principle, it should be swing beyond x0, because it will only stop when you have a pendulum. It will swing, and then it swing x naught, and then you continue to swing. So that is what I expect. It will not stop at x0 exactly. Okay, it would not stop exactly here. So you should expect to see some values to extend beyond this and then goes to 0. Okay, but in your simulation, we only allow, in your simulation, someone is making some noise. Yeah, sure. Good. Question. I'm happy to hear you. Yeah, yes. Yeah. Yeah. Yeah, so I think you got some point. I think you get some point. The problem with this is the initial condition is set in a situation where it does not allow you to see the whole picture. I think the initial condition is, if the initial condition is well set, then you would not have complications. So when x swing to x naught is not 1, is 1, but when x go beyond x0, it should become lesser. So according to your question, we should be at what again? Can you say it again? Yes, when x is larger than x0. Now at some point, v will stop, right? Where does v stop? It stops at some point where the energy become yeah. So at what x will the v become 0? No, at 1 and -1 it would not stop, because at 1 and -1 v will still be 1. So you have to use conservation. Yeah. 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 So it will stop at somewhere. Let us try to see. The total energy is not given in this sense. But can we see what is total energy? Not sure. But anyway, what I'm saying here is that let us plot anyway the solutions for XARR, which is going to from -1 to 1, and then you see the solution. So this is a solution. V solve is solve V. Okay, sorry. Solution for V is the 0th component. So I'm going to plot this and see what happens. Solve V. Okay, plot is not defined. I always do the same. Okay, so this is plot solve. Now what is the problem if this plot solve V? Let me try to see what is the problem. Okay, let me do it again. Okay, so I'm going to see, do I get solve? Okay, not solve V. Solve V, yeah. Solve V should give me a set of number. So it's an array, which is not true. Model in, okay, so this is the solution. Model, initial condition, and XRR. So let me print out this one. Okay, so this is true. So this is the solution. So I should take it as an transpose. So I forgot to take the transpose of this. So the solution V is the transpose of this. Okay, I think now I got it. Plot PLT, plot XARR, LV. Again, I got some problem. Let me see what's my problem. Okay. Print the solutions. Print SOLV. No, this is not this one. I think this is the one. Yeah, okay. So there's only one solution. Yeah, sorry, there's only one solution. So there's not two solutions. So I should not including this one. Yeah, no. Yeah, I think point solve dot t. If it's dot t, do I get anything? If it's dot t, just dot t. So maybe this doesn't look like it. If it's the 0th component, I got only one. Okay, so let me resolve this. Okay, never mind. Let's try anyway. Okay, so I'm going to plot this one and see whether I got anything. No, I think it's an error. 0. Maybe not this one. Maybe this is this one. Not again. Now it's a dimensional problem, okay? So I just have to fix because I sometimes get confused. Okay, so I want to see this one, whether it works. Okay, so I need a cell. So I put it here. Just print out thing. Okay, so this is not plotting. The reason is because the solve is not showing the correct thing. So this is not correct. So no one. Okay, so this is the array. I should take the transpose of it and then take the 0th column of this. So it looks better now. So the solutions, you transpose it, then you take the 0 component would be the solution. Okay, so in this case, then I plot XARR, this one. Okay. What happened? Okay, plot again. Okay, so PLT. Okay, so I got a graph. So this is the graph that is the same as Cheryl has obtained. So this is the solutions, which is the same as yours. Okay, but what I'm saying is that what happens that that should be beyond 0. Sorry, this is x0. This is x0. So the graph should actually hit 0, right? So it should stop at the moment, and then it should extend up to beyond 1. So somewhere here, maybe 1 point something, maybe 2 point something. So let's try and see. Okay, just try. I'm not sure whether this is working, but let's say 2.0, maybe 1.5, and make it 20, 30. Okay, so let me cut and place this one. Okay, so this is my solutions. Okay, syntax error pula. So x array, now this is 1.5 x0. So it's like this. So when it goes beyond 1.0, there's no, okay, so, okay. Now it looks like it is making some progress here. Maybe let me define this only, then I'll come back to you. Maybe I make it 2.0. So what I'm doing here is that I make sure that I have to obey to this initial condition. At x0, v is v0. But the other side, I don't stop at minus x0, but I make it to be larger. Like, so I make this endpoint of the Lin space to be larger because I expect the pendulum to oscillate beyond negative x0. And then you see this. So it is a solution. This is 0, so it's not going to go into here. So because the code is going to be like this, it is going to oscillate, and then it's going to be maximum at x0. And then it will oscillate until here. So it will stop at x0 equals to 1.5. Right, roughly somewhere here. Now this value is the point where the pendulum stopped for a while. Right, so it stopped for a while. That corresponds to the maximum of the kinetic energy when it's the kinetic energy is totally transformed into the potential energy. So from here, you should make the x0 to extend, but you do not know how much you extend to. So if you extend it to, say, not 2, but 1.5, then you get the solutions. Right? So it stops somewhere here, maybe less than 1.5. But then you say, how about on this side? Now this side you can't do much thing because the initial condition has to begin from here. So if you were to be smart a little bit, you may have to carry out another solution where your x0 begins from here. Then you have to make your x0 to be larger. But how do we make this larger? It is difficult at this point because all the while when we teach you how to use the initial condition has to coincide with the first values of the x that you put in to your Lin space. So, but the problem is that the pendulum at x0 is not beginning at x0, right? So it begins, well, now what I'm saying is that these questions is not well designed. Now, if I were to give you the maximum position where the velocity stops for a while, that would be best. Now, the question would be best if this is 0. Now, that would solve the problem because it tells you that when the object is released from 0.1, and is released with 0.1 at rest. So that should be an easy question if I were to make the initial condition to be velocity at x0 starting from 0, but instead of starting from 1. Okay, so if I were to give you this, right, v as x0 equals to 0 but not 1, that is to say the pendulum starts from the rest but not starting at 1. So if this is the case, that means that you release it from rest. So that would mean that the maximum amplitude of the pendulum would be just 1. It would not go beyond 1. So it causes some problem here because the initial conditions, the initial condition that is given here in the Python code using this ODE init does not allow us to slot in initial condition which is not 0. Okay, let me see what Kenhui was saying. Can we say that in the original question, the initial condition is v at x0 equals to 1? Yeah, I think this is correct. So this, okay, so according to Kenhui, in the original questions, the initial condition is v at x0 equals to 1. And at x0, at minus x0 and x0, it will be 0. I think that is a better corrections. I think that is the correct one. This is original one. V at x0 equals to 1. Yeah, okay, so v at x equals to x0 equals to 1. Okay, so the original question says that x0 equals to 0 and v at x0 equals to 1. Okay, so there are two possibilities, right? So either I say the pendulum at the beginning when x is equals to x0 is at rest, as v0 is at rest in the beginning and then release from rest. Or the other way is to say this, that is initially the pendulum is at 0 position, v at x equals to 0. When v at x equals to 0, then the velocity is equals to 1. So according to Kenhui, this is the original questions. Okay, so if this is the original questions, then things become slightly less complicated. Okay, so let me save this. Now assume that we follow Kenhui's suggestions. I may have made some mistakes in the process, but I think this is the original question that I was preparing. x0 should be at 0 initially. So this should not be 1, this should be at 0. Okay, so if this is the case, then it becomes easier. So in that case, your x0 is 0. Okay, so your x0 is 0 and it's not 1. So x0 is 0. This is not 1. And then this is v0 is 1. Okay, so now let me tidy up what I have said. I said a lot of things I may have made you confused, but now we will agree that the initial condition is that x0 is 0, v at x0 is equals to 1. So that is the object, the pendulum is swinging. When it passes through the bottom, which is x0 equals to 0, the velocity is 1. That v at x0 is the highest velocity. Right? The highest velocity always occurs at when it passes through the equivalent positions. Okay, so let us try to put this initial condition back, and then we should be able to get the solution, which is not like this complicated. So your x0 is 0 and v0 is 1. So that should go from x to x0. Okay, x to x0. And then let's see what happened. This is what I expect. No, only one solution. Why is there only one solution? X to x0, v0 at 1. Then how about the range for values of x? Since the x is, okay, let me see what Chino was saying. Then how about the range for values of x? Since x0 equals to 0, the range should be from minus 0 to, yeah, okay, you're right. Yes, yes, yes. So the velocity is beginning from 1. Okay, okay. So that is the problem. the x0 is 1. So, okay, I think this is, the x0 should be 1, right? So x0 actually, when I design initially, when I initially design the x0, the x0 is supposed not to be the initial condition, okay? The x0 is supposed to be the amplitude. Okay, so it has an amplitude, and then at 0, it could be like this, okay? So I'm making a correction again, so that is my problem. So this is the original questions. When the velocity, this is initial condition, okay? When x0, when x is equals to 0, the velocity is 1. I think that is the original questions. And x0 equals to 1 is not an initial condition. X0 equals to 1 is just to say it is the amplitude of the oscillation. So the x is oscillating between -1 and 1. That is its amplitude. Right? So I think now the problem seems to be fixed. Okay, so I was confused just now because I thought that the x0 is the initial condition. No, it should not. There's only one initial condition. That is when v at 0, it is 1. Okay, so that is the constant. Right? This is amplitude, and then this is the initial condition, and the initial condition should be like this. At x equals to 0, so you start off with 0. I think this is the correct one. Then you go to 1. I think this is what Cheryl was referring to. So your solution only covers the positive side. That is, you start off with 0. When x is 0, v is 1. So that is what you say. When x is 0, v is 1. And then you swing from 0 up to maximum 1. And then you got one solution. So this solution is on one side only. Right? So it starts from at 0. And then it goes to somewhere. So at the point here, when the x become 1, the velocity will stop. So that is true. Okay, so you have only one solution that is on the positive side. So like what Cheryl was showing, in order to get the other side of the solution, this side of the solution, you have to do another solution. So you start from x0, then x0 goes to 1. Then you have to find another side of the solution, which is on -1. So if we were to do this, then this is how you do it. Where am I? Okay. So then you have to do another solution with another solution, which is like this. Okay. So you have another solution, XARR. I'll call this positive 1. Then this is positive solutions. And then this ARR minus solutions. It goes from minus. Yeah, questions? I couldn't hear you. Can you say properly? So you have to do 2 parts. Yeah. Okay, so let me show negative plus and positive 1. Okay, so this is how I do it, right? So there are 2 solutions. One solution is your x is running from 0 to +1. Then this is your solution. Okay. Then you have another solution where your ARR is to begin from 0 up to -x. Okay. So this is a negative solution, and I call this solve x, where the solution is for x ARR minus. This is x ARR plus. I'm not sure whether this is allowed. I think the name may not be allowed to be having positive or negative. So let us try anyway. So no, the syntax error, I am not allowed to use the symbol plus or minus as a solution. So this should be plus, and this should be plus. So I replace the plus with a p, right? So with a plus, and then this is minus. So I replace this with a minus. Okay, so wait, I think someone is saying something. So this is plus, this is minus. So when I plot the button, this will be plotted, this will be plotted. So it will combine both solutions. XARR, this is minus. Okay. So I have solve MVM. Okay, this one solution M is not set here. Okay, so solve M minus. Okay, so I have both solution, but Vp and Vm. No, it looks like this is from 0 positive, this is from 0 to minus. So this is the solutions for XARM. Plot solve Vm, plot Vm. So both will be plot. I'm seeing only one part. Okay, let's see. Anyone say anything to me? No? Okay, so let's come back to here. We are waiting a lot of time. So now this is the part which is positive. So this is a positive solutions, and then this is supposed to show me the negative solution. So which is on the other side. Do I get the negative solutions? No, I don't get the negative solution. Solve Vm XARM. So that should be these solutions on this side. But why don't I get the negative side? Solve Vp, Vm, initial conditions. Yeah, it's the same. Initial condition is the same. Subtract from 0. And I'm going to minus 50. So let me clear these things. And then run it again. Okay. So NP is not defined. Where is NP is not defined? Okay. Import numpy as NP. So there's an error. XARR is not defined. Here, XARR is not defined. So I'm going to do the troubleshooting here. Plot XARR, yeah, POT plot, yeah, here. So that should be XARRM instead of XARR only. So this is a solution. This is a solution for XRRP. So I have to combine the positive solution and the negative solution at the same time. Do I get? No. Yeah, I get. I have to plot both the solution for the negative one and also the solution for the positive one. Okay, so this is the positive one. Then this is a negative one. M minus, stand for minus. This is for minus. So this is to plot the positive solutions, and this is to plot the negative solution. So let's see both sides. Yeah. So the problem is that you have to solve it on both sides, and then you start off from 0 and then you end up with 1. Okay. So now it's fixed. The solutions is that the boundary condition should be this. V at 0 should be 1, and then this is not initial condition. This is to say that the pendulum is oscillating between -1 and 1. So just have to put this into the initial condition. And when you put this into the initial condition, you don't solve it just as it's a first order differential equation. You have to understand the pendulum physics. That is, when you set the velocity at 1, then x not equals to 1, then the pendulum will actually oscillate between -1 and 1. I think that is what we are expecting. We have mv squared. Let me see. Half mv squared equals to half kx squared. Yeah, I think this is consistent. Now, so if you look at the conservation of energy, the potential energy is half kx squared. The maximum of kinetic energy is half mv squared, where v is the largest when it goes to the center. So the maximum kinetic energy is just half of m, and the maximum of the potential energy is also half of k. And since k and m are equals to be 1, then this question is now consistent. That is, the maximum kinetic energy and the maximum potential energy are the same. That is, the potential, the oscillator will oscillate between -1 and 1. So then you put in these initial conditions. That is, when x equals to 0, v is 1. But then when you solve it, you start off from 0 up to 1, right? So this is the right hand side. But then you realize that this is only half of the solution. You have to solve another half. Then you combine that to get this. So you have two sides as a solution. So Now, just to make you less confused, I'll save this solution in the assignment. Then you can try to just upload this as. I think this is part of my fault maybe because I didn't check the questions very carefully. But anyway, this is what we want to do. It's already 1 hour. So we are wasting an hour to solve it, but at least you try to learn something. Now this is a solution that requires a correct initial condition. Okay, and then you also need the questions to be consistent in the sense that the energy has to be conserved. The total energy in the kinetic energy and the potential energy has to be conserved. Okay, so now the question is conserved in total energy, and then is also consistent with the initial condition. So this is, if it's causing any confusion to you, please don't hesitate to ask me to do it, to explain to you again privately if you want to. So it's 3:58. So maybe we take a break now until 3:405. So I'll let you to do the this one. So you take the attendance. Then I'll see you at 4:05. Okay. Then we continue. That's all for the moment. So I'll see you in 5 minutes time. Okay, so let us continue on this part. Let me bring down my screen a little bit. Okay, so that should be better. Now, to do the second order differential equations, this is what you need to do. Of course, you need a sin pi integrate. Is it sin pi integrate? Let's see. Then you need an ODE. Maybe you don't need sin pi integrate. Maybe this is not required. I'm not sure. I think it shouldn't be required. Then, of course, you need to solve the second order differentiation. So you need ODE integrate, and then you need NumPy, and then you need Matplotlib to plot your graph. Now we set up the initial condition. Okay. So no, initially we initialize the problem. When you initialize the problem, that means this is a question you want to solve, and you want to define the constant. I think when I say initialization, it means you define the constant. So you need to know what are the values of G and L. So of course you first say G is 1.8. Now just ignore this NT for the moment, okay? Then this is your G, and then this is your length of L. After that, what you need is to define your omega. Right? Omega is the frequency, which is square root of G over L. So this is your omega. Okay, so that's how you do it. Now once you define the constants, and then you have to look at the physics, right? The physics says omega is a frequency, and then from the frequency you should be able to deduce what is the period. Now the period is related to the angular frequency, T equals to omega over 2 pi, right? So once you know the frequency, you should be able to deduce the period. So the period and frequency are related. Now what is important here is that you would define your period as 2 pi over omega, and this T, as I mentioned many times, is the time scales that characterize the oscillation. So when you do the simulation, you want to simulate for how long. So you should define the length of your simulation time in units of the period. So this is a period. So how many periods I want to oscillate? Well, I just want to show that it oscillates at least for 5 periods. Okay, so I think this NT is just a number to say that I want to oscillate for how many times? 4 times, 3 times, whatever. Okay, yeah. So I need to define then how long I want to do the simulations. Okay, so how long I want to do the simulation has to be expressed in unit of time. So this is what I'm saying. Once I have defined the period, then I say this is my linear space for the time, and is to span from 0 up to 5t. Okay, so I define NT as 5 so that I can change easily the length, total length of my simulations. So I said I'm going to solve these differential equations for t starting from 0 up to 5 period. So this is always the thing that you would do when you solve this differential equation. Just choose the linear space in the independent variable. Then you define your model, right? So what should go into the model is this. You have to provide and tell the model what is your independent variable and what is your dependent variable. Now this param 1 or param 2 is optional, okay? So you can specify param and then pass the values of param to this argument. Now if you don't want to do it, then it's fine. You can still do it. You can just declare your parameter outside the model, okay? But here I do it such that the values of the external parameter are passed into the model through argument, okay? So what is this param to be passed in? That is the values of omega, okay? So this is the values of omega, which is defined inside here. So the omega is defined to be like this number, but the omega defined outside and the omega defined inside, in principle, are two different things, right? This omega that is defined inside the model is what we call local variable. So in practice, there's no difference between this omega and the omega defined outside. But I just want to demonstrate to you that there's a flexibility for you to use the extra argument in the arguments here, in the ODE INT, in case you need to plot many different parameters. So for example, later on, if you were to do an oscillations like this, so in this case, each of the solution has different parameters. For example, this is the parameter where the oscillation, what we call the damping ratio is like 1, this is like less than 1, and this is like less than 1, this is equals to 1, and this is larger than 1. So in case you need to do solutions for same differential equation but with different parameter, then you may have to use these extra parameters to define your model. But for this simple harmonic motion, this is not necessary, but you will see its usefulness later on when you solve the damped oscillations case. Okay, so what is important, the mandatory thing is what is your dependent variable and your independent variable. So this is what we want to solve. We want to solve theta. So your dependent variable here is your theta. So this is your theta. So the theta is the dependent variable. And now, since we are solving a second order differential equation here, this is to be different from the first order differential equation. In the first order differential equation, maybe let me go back to the assignment that we discussed just now. Now, when we solve this first order differential equation, remember, when you define the model, you have only one dependent variable, just one, because it's just first order differential equation. You just need to use the model to generate dv dx, right? But for the case of a second order differential equation, you need two things. You need not only to generate the first order differential term, you also need to generate the second order differential term. Okay, so you need two independent variables. That is, other than theta, you also need d theta dt. Okay, so in the previous case, for this one, you just need the original dependent variable v. You don't need dv dx. But here, in order to solve the second order differential equation, the independent variable is made up of two things. The first thing is the theta. The other one is theta dot. Now, theta dot here is just an defined to be d theta dt. Okay, so when you solve second order differential equations, you have to sort of like decouple the second order differential equation into two first order ODEs. So these statements and these statements which is two statements, are equivalent. So you define theta dot as d theta dt, then d2 theta dt square equals to minus omega square theta, and then is just equivalent to the second statement. That is, d theta dot dt is equals to minus omega square. So one statement here has to be split into two equivalent statements. Then you use the ODE, you use the ODE INT functions to generate the expression of theta dot and d theta dot. Okay, I think that is the idea. So in the model, you have one dependent variable which is made out of two components. The first component is the theta, and the second component is theta dot. So what you do is that once you enter the model, you assign the first component in the variable that goes into model. The first component is assigned as the values for theta, and the second component in the dependent variable is assigned as theta dot. Now, once you have assigned the definition of theta as the first component of the independent variable and theta dot as the second independent variable, then you would want to define your differential equations here. So the only differential equation that goes in is d theta dot d theta is omega square theta. So we call this d theta dot d theta theta dot dot. So this theta dot dot is just representing this omega minus omega square theta. Okay, so let me say it again. To translate these second order differential equations into ODE interpretation, ODE INT, you slot in the expressions, the initial conditions, or the initial values of theta and theta dot. Then you define the second order differential equation expression, which we call it theta dot dot. Now at this stage, everything is now well defined. In the model know what is theta, the model know what is theta dot dot. Then the model also know what is the expression for theta dot dot. And you want the model to return theta dot and theta dot dot. So that, see, remember, theta dot is the first derivative of theta. Theta dot dot is the second derivative of theta. Now, using the knowledge of theta dot and theta dot dot, and put these values into the ODE, what you get is theta and theta dot as a solution. So basically, the ODE INT is to integrate theta dot and theta dot dot. Right? Theta dot is d theta dt. Theta dot dot is d2 theta dt square. So integrating theta dot gives you theta. Integrating theta dot dot gives you theta dot. So once you put into the model to define theta dot dot and theta dot, then the expression of theta dot and theta dot dot that is returned to ODE INT will be integrated. So ODE INT sort of like integrate theta dot into theta, and it also integrates theta dot dot into theta dot. So when you solve the ODE INT, you get two outputs. The first component of the output is the theta solutions. The second component from the ODE INT is the theta dot dot. So this is how you do the ODE, second order differential ODE in Python. Right? So you have a second order differential equations, you break it into two, then you define this theta dot and theta dot dot in the model. Then you call the ODE and slot in the expression of the model, put in the initial condition for theta dot and theta, sorry, put in the initial condition for theta and theta dot. Then, of course, you have to specify your linear space, which we already defined to be 5 times the period. Then the ODE would provide the solution for theta as its first component and theta dot dot as its second component. Okay, so let us run it one by one. Maybe I'll just add in this one. I'm not going to write everything from scratch, so I just want to show you how things are done. Okay, so maybe I just move this towards here. Okay, so I'm going to run this, right? So I've explained to you how you define your differential equations in model and how you call the model. Now I have not mentioned this one. This is just a constant, right? This is a constant. I define constant theta dot as some initial value and theta dot dot as some initial value. So this is the second order differential equation, describes a pendulum. So in the beginning, you have to tell me at time 0, where is your theta and what is theta dot. So you displace the pendulum at t0, you release it. So the theta at t0 refers to the initial displacement. So how much you want to displace. So you cannot displace it too large. Maybe you just displace it by 5 degrees or 2 degrees or 4 degrees. Okay, so I say I displace it by 5 degrees and I let it go. When I let it go, what is the initial velocity of this pendulum? The initial velocity of the pendulum initially is just 0 because I release it from rest. So theta dot, which is the initial condition that should be supplied to the second order differential equations, is interpreted as the rate of change of angle. So theta dot, in a sense, is an angular velocity, right? Because theta dot means the angle change with respect to time. Initially, when you release it from rest, it is not moving at all. So the rate of change of the angle with respect to time, which is the angular velocity, is just 0. So theta dot is 0 in the beginning, and theta 0, which is defined as this one, initial number, I take it to be 4 degrees. Right? So 4 degrees in unit of pi is 4 times pi over 100 degrees. So I'm expressing this as angle in pi, but I use 4 to express my, it's a 4 degree. Right? 4 degrees times pi over 80 is just the unit of 4 degrees in radian. Theta dot is the initial angular velocity, which is 0. And then the parameters is just, no, I think the parameters doesn't matter. Okay, so it's just a number. So even though you don't pass a parameter, it will still work because omega is already defined outside. Then the initial conditions is important. Right? The first initial condition is referring to the initial condition for angle. So theta dot is for angle. So this theta dot will goes in to the model, and theta dot is a 0 component of this. So theta dot value will be assigned to the values of theta. And then theta dot dot, when it's go into model, the first values of theta dot dot is assigned to the second component in the dependent variable. Okay, so this theta dot will take in the values of the second initial condition. So this theta dot will be taken up by theta dot when it goes into the model loop. So now we are ready to call the ODE. You use the ODE to put in the model. Then this is the initial conditions. It comprises of a tuple of 2 initial number. Then this is the arrangement. So you press the button, you find there's no error. So let us print out the solution again. The solution SOL is like this. So this is a solution. It makes up of 2 columns, right? So the first column is referring to theta. The second column is referring to theta dot. So let me try to extract the first column. So this is to extract the transpose of it, and then this transpose has 2 rows. Okay, the first row is, let me see, the first row is theta up to, no, there are too many, But anyway, what I'm saying is that if you check the this one, we check the shape np dot shape, the transpose of the solutions is 500. Right? The first row is the theta, the second row is the theta dot, and this is obtained from transposing the solutions. Okay, dot. So now I have printed out the solution dot. Then we know that the first component is the theta solution. So this is a theta solution for the 0 component, and then this is a theta dot solution, second component. So now we are ready to plot what? Plot TARR, the linear space of time, and then theta solution. So this should show me an output which is just the solution I expect, which is the ODE solutions, oscillations with some constant and phase shift. Okay, so let me press the button. I would like to see an oscillation curve. There's an error because of PLT. I keep on forgetting this PLT thing. Okay, so I have a nice oscillations. Now you can also plot the oscillations with respect to theta dot. So this is a solution for the angular velocity. Right? So angular velocity, if you refer to these expressions, if theta is this, then theta dot is also an sinusoidal. It's just that theta dot is cos instead of sine. So the solution for theta and theta dot should have a relative 90-degree phase shift. So when I press a button, I would see two solutions. One solution for theta, one solution for theta dot, and these two solutions should be shifted by 90 degrees. Right? So it's true, right? So, but they have different amplitude, right? The amplitude for theta is theta dot, and is a theta naught, which is 5 degrees. And this blue color, I think, not sure which one is blue. So the other one is the theta dot. The theta dot is a speed of oscillation, right? So the maximum theta dot occurs when the pendulum swings to the 0. So you can calculate what is the values of theta dot from the conservation of energy. But here we don't do it, right? So that is how you solve the second order differential equation, by doing this this method. So the trick is this lah. Okay. Let me repeat again. So you put into the model two dependent variable. The first dependent variable is theta, then the second one is theta dot. Then you define the expression for theta dot dot, and whatever you do between the model, finally what output is theta dot and theta dot dot. I think this is a trick. Okay, so if you are ready, then you can go to the next bit. Now this is another example. The differential equation is slightly more complicated. So it has, this is the ordinary simple harmonic, which we already solved. Now let us try to put in this 2c omega. So you have additional constant c is in addition to omega, and then you also have to define the theta dot in the model function, right? So these equations accordingly would then broken into two equations. So first equation is always the definition. So you define theta dot. Then this d2 theta dt square, in terms of theta dot, is just d theta dot dt. So d theta dot dt is just d2 theta dt square. So let's see what is the d theta dt looks like. So when you differentiate it, then no, you don't differentiate that. This is nothing but just a copy of these equations. Okay, but then here we just do some simple adjustment. Here, once you differentiate the theta, this theta and this theta dot is the same, right? So here d2 theta dt square is d theta dt, and on the right hand side you have a term d theta dt, And what is d theta dt? D theta dt is just theta dot. So wait. Okay, so here we just express the d theta dt in terms of theta dot. So what we're going to do is that we're going to define theta dot and theta dot dot. This is theta dot dot. D theta dot dt is theta dot dot. So theta dot dot is just negative omega square theta minus 2c omega theta dot. So what I'm going to show you is how you translate this set of three equations, this set of two equations. The first set, and the first set is the expression for theta dot. And the second set is just this line. It's just this line. So as usual, in your model, the dependent variable is made of two components. The first component is the theta. The second component is theta dot, right? So now this line of theta and theta dot is just this expression. So normally for theta dot, you don't need to do anything, right? It's always defined as just theta dot is just d theta dt. Okay, so now we have to translate these equations. So what we need is that we have to define theta dot dot. Theta dot dot is equals to minus omega square theta minus 2c omega theta square. So here it is. Theta dot dot is just minus omega square times theta, where this theta is just the values that's obtained from the first component of the dependent variable passed into model, right? So theta dot dot is minus omega square theta minus 2c omega theta dot, right? So this theta dot is just the second component in the dependent variable that is passed into model. Okay, so of course before that you have to define what is your c is a parameter which is chosen to be some number which is less than 1. It represents under damped, equals to 1 is critically damped, larger than 1 is. So we are going to see how the graph looks like when you change the different c, right? So we're going to oscillate for 3 periods, and then these are just a number that is, these are just a number that is the same as in the previous case. So now we have finished defining the model. So the next bit is just to use the ODE, which is very simple, right? So the ODE is just the same. You put in the model, so the name of the model still named the same, but here the initial conditions have to be put in. I think the initial condition in this case is the same. So you have a pendulum, you release it, theta at 0 is 5 degrees, and it is released from rest. So there's no change in the initial condition. And arguments, well, the arguments here now has 2 more arguments. Instead of just omega, you have another number which is called c. So you pass the values of c, xi, into the argument. Then this number will then be passed into param 1 and param 2 into the model, where param 1 is a number which will be defining the values of omega inside model. Param 2 is going to define the values of c. So the values of c inside the model, again as I mentioned earlier on, is independent from the c and omega defined outside the model. This is called the local variable inside the model. So by doing this, by using param 1 and param 2, which values are passed through the ARGS arguments into the model, could then be changed independently. Okay, so later on we are going to change the parameter of the c from 0.1 to 0.2, 0.3. So by doing that, you'll be able to see how the different solution looks like. So you can plot 3 solutions, 4 solutions for different c in the same graph. But we are going to see that later. Make sure that you understand the how to define the second order differential equations. So once you have done that, then the model would return the theta dot and theta dot dot. Then these two again will be called by ODE. So ODE will read in theta dot and give you theta as a solution, first component solution, And ODE will integrate theta dot dot to give you theta dot as the second component in the solution. So you extract the theta as the first component in the transpose, the first column from solution, and then you extract the second column from the solutions, then you plot it. Right, so you get this solution, which is very nice. Now let's just try to see how do you change the C. Right, so if you change the C to become, say, 1.0, then the solution will look like this. And if you make it to be, say, 0.9, then it looks like this. So can you plot many solutions of C in a single graph? Now, in order to do that, you have to make use of the parameter argument, right? So here, the parameter argument, let me cut and paste. So here, the parameter argument is C, right? So C is 1, 2, 3, 4. So this bunch of line will define the values of C, solve the differential equation, extract the theta dot, and then plot it. Right? So if you want to plot, say, 3 different solutions with 3 different C, then you can just write a loop, and then you just change your C. So for example, say for C in 0.1, 0.5, maybe 1.0, and maybe 2.0. Okay, then you write a for loop, and make sure that when you write the for loop, you make a tab, just put all these actions or all these commands to be looped inside the C. Then once you have finished plotting everything, then you just plot it all in one. So by doing this, you're able to show different C at different time, right? So you have 3 different C, then you can do a better job by, say, put a label. Label is C, okay? Values of C equals to plus string, and string convert the values of C into a number so that you can see the label. And then you plot the show. Before you plot the show, you also ask it to plot the legend. Right? So the legend will give you what are the numbers. Okay, so C equals to 0.1, which is on oscillations. And then when C goes to 2, it becomes a damping point, over critically damped. So 1.0, which is the green color, is an critically damped solutions. So as I mentioned, critically damped solution is a solution where the pendulum would not even complete one cycle. Okay, when C is less than 1, then you have more cycle. So for example, 0.5. So 0.5 is that you have this cycle, but then it dies off very easily. Right? So at least it complete one cycle. So one cycle means, so this is one cycle, one complete solutions. Okay. Now you can try to do the same thing here. This is another example where the solutions would involve, well, this question and this question are very similar. Okay, so this is also a pendulum questions, but sorry, this is a damped pendulum questions. So here you have d2 theta dt proportional to minus omega squared theta. So this term is the oscillation term due to the gravitational force, and then this is the pendulum term. So the important thing is that for the gravitational term is proportional to the negative of displacement, and then the damping term is proportional to the d theta dt. So if you look at this expression, you have a G term, which is, well, this G term and the G term here is different. Okay, but anyway, what is important here is that you see that the pendulum term has the damp term is proportional to d theta dt. Right? Here you see this is dy dt. Right? So left hand side is d2y dt, right hand side is dy dt. So this dy dt with a negative term and with a constant given by k over m, mathematically it is equivalent to this. Right? So this term is also proportional to minus 2 omega c theta dot. So when you see an d2 theta dt square proportional to minus some constants times the rate of change of the displacement, that usually refers to a pendulum. So not pendulum, the damping term. So the damping term in this case is the same. So this is the damping term. So what is this? This is referring to the dropping of an object from rest under gravity, and then it's experiencing and damping. This damping is given by K. So K is the damping term presented to the object by the medium, and M is the mass of the object. Okay, so this is a second order differential equation which you can easily incorporate it into the ODE. Then you solve it. Then here is just a simple analytical solution to tell you that the second order differential equations of y, when you solve it analytically, this is what you get. The solution is v and also y. Now let me remind you again, a second order differential equations, when you integrate it once, you get dy dt. So dy dt is also a solution. Then you also have a solution in terms of y. Okay, it's just simply like this case. The original second order differential equation is d2 theta dt squared. So when you integrate once, you get theta d theta dt. That is one solution that is useful. And also you have theta as a function of t. Right? So you derive two solutions. So here d2y dt squared equals to this one, describes the how the distance of the dropping object changes with time. So when you integrate it once, you got dy dt, which is telling you how fast the velocity change with time. So that is what dy dt means. So by integrating this, you will see you get dy dt. In addition to that, you also get the y as a function of t. So the purpose of solving this equation is to obtain y as a function of time and dy dt as a function of time. Right? So dy dt is how the velocity changes with time, and y is how the distance travels change with time. So if you solve it analytically, you find that the velocity change with time through this very simple relationship, which is just a terminal velocity relationship. Like the object will just keep on going until when t becomes very, very large, specifically when it's larger than a few tau, where tau is a constant given by the ratio of m over k, then the velocity will tend towards the terminal velocity. Then when you integrate dy dt again, see v is dy dt. When you integrate dy dt again, then y as a function of time is given by this expression. So it is a distance that is keep on increasing. Right? Under gravity, the distance will just increase proportional to time square. Remember, v equals to y equals to what is that? You remember the kinetic equation? Y equals to ut plus half at squared. Right? So under the gravity, object when it's dropping, it increases as parabolically in terms of t. So y will be increasing proportional to t squared. But under the drag force, the behaviors of y changes with time will be slightly less serious than t squared. The t squared is changing. T squared means y is increasing and is in the parabolic. But if you add in the term, the terminal velocity term, or the drag force term, the tau, it modifies the behaviors of how y change with time. So it modifies y change with time as function of square of t into this form. So when the tau, which is describing the terminal velocity, if it's becoming lesser and lesser That means if it's dropping in a medium where there's no drag force, in that limit, what happens is that K become very, very small, right? So K, in terms of the physics, is describing how strong the drag force is affecting the change in the dropping, right? So if there's no drag force on the object, K will be 0. So in K 0, then that means that will be just dy dt equals to dy dt squared equals to G, which means it is just an object dropping freely under gravity without drag force. But if you switch off the drag force, then that would be the free fall. But if you switch on the drag force, that is when K is not 0, then this will modify the behavior of Y. How would it define, how would it modify? It would make the Y to drop less than the free fall. The free fall is Y proportional to T squared. So if you switch on this K, then Y would change less than T squared. It is like this. And in the limit where the K is switched to 0, tau would go to infinity, right? So the tau would go to infinity because tau is proportional to K, right? K if switch off to 0, tau to infinity, then this term will become 0. Then this term will be, then this term will drop to 0, and then this whole expression of Y would then tends towards the behaviors of a parabolic curve where Y would varies as a function of T squared. So this is what you can see. So if you run the code, you see that now this is a solution of Y as a function of T for different values of the drag. But when drag become very, very small, which is the blue color thing, what happens is that you don't see, you see this one. Now what is this graph tells you? This graph tells you it looks like a parabola. Parabola means Y is proportional to T squared. Right? So when the drag force is very, very small, Y change parabolically. And this is what you expect in the case of a free fall, where the drag force is minimum. But if you drag first become large, you switch on the drag force, then the Y would change less as a function of time, right? So you see the other curve. When you see other curve, the K would be different, right? So the K would be not 0. So this represents the case where the drag force is present and is affecting the change of Y as a function of time. So anyway, when you switch on the drag force, the behaviors of V would be altered, right? It would drop less fast as compared to a free fall. A free fall is a limiting case. Now I'm telling you a lot of these things, which is not directly relevant to the solution, is that I want you to appreciate physics, right? You look at the equations of motion, you should always be able to try to interpret this and interpret, for example, what happens to the behaviors of the solution in certain limit. So this is a physical situation. K represents the drag force. You set off drag force to 0, it should fall back to free fall. And you expect, you know what free fall looks like. So you would also then know if you just switch on the drag force, then the free fall will modify. And you expect the modification will be such that it will drop slower. It will drop slower. And indeed, when you see your solutions, you see the solution, it looks like this. That is, the line for Y with non-zero K is lying below the free fall case, which is consistent. Now, if you solve your code, and then finally you find that when the K is not 0, the solution is on top, well, on the left-hand side or on the above of the free fall case, then you know your physics is wrong. You know that the solution is wrong. So solving differential equation in a way is easy because it's just technical. As long as you put in the code correctly, then you get the answer. But what is difficult is to be able to relate your differential equations or your solution to the physics. Right? So if you get the physics right, you've got a solution, you always check your solutions and see whether the solution tallies with your physics. Just like in the previous case, the tutorial 8.1 thing, right? So tutorial 8.1, I just want to make sure that the physics is right, the conservation of energy is imposed. So if you get the solution right, but the physics is wrong, then it's wrong, okay? Even though mathematically is correct. So try to appreciate the physics when you solve the differential equation. So once you know the physics well, when you solve your equation, you'll be able to tell whether you are solving it correctly or not, okay? So this is a whole bunch of equation, which is quite easy to solve. I'm not going to type in detail since we don't have time. So again, you you define your gravity, you define your constant of drag force, then you define the terminal velocity. Now I define this tau and t is because I would want later on to overlap my numerical solution onto the analytical solutions to make sure that the analytical solution that I get and the numerical solution that I get agree with each other. Okay, so I'm going to plot two things. I think I'm going to plot. I plot two or I plot one. Maybe I plot two. Yeah, I think one is the plot of the solutions, and do I plot the analytical solution? No, I think I throw it away. So I didn't plot the analytical solution. Anyway, this is the numerical solution only without the analytical solution. Maybe in the next part I do plot the analytical solution, but maybe not. Okay, but never mind. Okay, so let's see how you do it. So you define the constants here, then you define the model. So here the dependent variable has two numbers. The first number is y, and the second number is y dot. Right. So this second order equations. So we want to know what is y, and we also want to know why is y dot. So y is the first component in the dependent variable. Y dot is the second component. Okay. So once you define the y and y dot, then you look at this equation. So left hand side d2y dt squared is just y dot dot. Right. Y dot dot has to be defined to be g minus k over m y dot. Okay. So I define here y dot dot as g minus k over m y dot. So this line is just to translate these differential equations. Okay, but you have to be careful. This is not to be called d2y dt squared, but it's to be called y dot dot. And y dot dot is defined in turn in terms of y dot. Okay, then you slot in the initial condition for y and y dot. Right, y dot is equals to y naught. So y is the initial condition. You start off with 0 or some high level the position is 50 meters away, or normally we set it to 0. Then you release it from rest. So initially y dot at 0 is referring to the initial velocity, which is taken to be 0. So the initial velocity is 0, initial position is 0. So these are the very simple initial condition for y and y dot. Okay, so y and y dot is the initial condition. Then I have to decide how long I want to simulate the dropping. So what I'm saying here is that the situations of the pendulum, of this terminal velocity, the time scale is defined in terms of tau. Right? Tau is the time that appears here. So it's defined to be m over k. So this m over k has a unit of time. That means once t exceeds tau, then the velocity would be arriving at half, almost half of the terminal velocity. So you want to express your total length of simulation t in terms of how many tau. Right? So the tau is defined to be m over k, and then I decide that I want to simulate for 4 tau, which is the total length of simulation. So object is dropped, and then we just keep on dropping, and then I want to see the solution for distance for a length of 4 tau. Then this is my time scale. Then I would like to see how the time scale, how the solution change for different values of the dragging constants. So the solutions is ODE, where you put in model, then you provide the initial conditions. Now here, the initial condition changes with different k. Right? So I put the initial condition to be, sorry, the initial condition is the same. Like it's y naught and v naught. But I pass the parameter in terms of the argument. So in these params, g is constant, m is constant. So this gkm is going to go into the model. So param is g, param 2 is k, param 3 is m. So m and G are not going to change, it will be the same. But param 2 would change, right? So values of K will take on different values. Then every time when it goes into a different loop of K, the values of K in the param will change. Then these values of K will be passed through the arguments into the model. Then the rest is the same, right? The first solutions is the solution for Y, then the second solution is for Y dot. Then you press the button, then you see different solution, right? So this is how the velocity, the values of velocity changes with time. And indeed, this line show that after a few tau, the velocity enters an terminal velocity. So these are the velocity which is experienced by having less K, right? So these three lines are referring to the cases where the K is very light. That means the resistance or the drag force from the medium is very less. But if the K is very large, then the pendulum will just arrive at the terminal velocity very fast. So this is the terminal velocity, and this is the case where the dropping is very similar like a free fall, where the drag force is minimum. And this is how the solution looks like. So as I explained, these are the free fall case where the Y changes as t squared. But if the pendulum, if the drag force is large, then they would be much different. Okay, so it's 5 o'clock now. So I think you should be able to do the assignment Q2. So you have the time to solve these equations tonight. Just make sure that the deadline is still available for you to do this. I think so. Today is Friday. I think you might have another. Yeah, I think you should still be able to do these questions. Okay, so there is a assignment number 10. So assignment number 10 is kind of difficult. So maybe you don't do the assignment 10 at the moment because take a break. Okay, so I will delay the submission deadline for assignment 10 until I finish discussing all other second order differential equations. So I'll let you to have some time of rest. Next week, Tuesday, we'll continue to discuss one more example of these second order differential equations. Only then I'll ask you to do assignment 10. So hold on your assignment 9 or assignment 10 at the moment until later lah. So I think this is assignment 9. Assignment 9 is not at the moment. I think assignment 9 is kind of difficult. Let me check first before I let you go. Assignment number 9. What was assignment number 9? Assignment number 9. Assignment number 9. So how does assignment number 9 looks like? Assignment number 9. Assignment number 9. Well, anyway, I think assignment number 9 is a difficult one. So I'll switch off the assignment number 9. You don't do it. You do it only by next Tuesday. Okay, next Tuesday will be fine. So I hide it, so you don't need to submit. Okay, so any questions before we stop here? No? So if there's no more question, then we stop here at the moment. I'll see you again. Try to do the assignment yourself, okay? So there will be only 1 or 2 small assignments for you for during the weekend. Okay, that's all.